Now question 12. This is a longer one. We show that this function here is an eigenfunction of both Lz and L squared, L hat squared, where L hat squared is given here, which is the angular part, angular part of the Laplacian. And we derive the corresponding eigenvalues. To derive the corresponding eigenvalues, you may use the identity given here. And such is the case with exams. You're generally given formulas and things like that to help you along, and in this case it's no exception. And for B, consider a function given here where A is a constant and AO is the Bohr radius. This is the hydrogen atom energy eigenfunctions with value minus ER, which is a Rydberg over 9, where ER is a Rydberg energy. Combining the information with the results from A, specify NLM quantum numbers of this eigenfunction. Show that a suitable value of the normalization constant is given here by A. Is the value uniquely defined? C, calculate the expectation value of x squared plus y squared equals r squared sine squared theta in the state defined by the eigenfunction here, sine. Now, psi. From B, you may find these integrals for B and C useful here, the standard integrals. Now, going on to the answer, A, applying the Lz to the function gives 2 h bar in the function. So the eigenvalue of Lz corresponds to this eigenfunction is therefore 2 h bar, which means the magnetic quantum number of m equals 2. Now applying L squared to the function gives you this. Now first term can be simplified using the given identity, and the second term is trivial. So we end up with 6 bar squared multiplied by the function. The eigenvalue of L squared corresponds to this eigenfunction is 6 bar squared, which means the orbital angular momentum quantum number is L equals 2. Now moving on to B, the normalization condition insists that integrating over infinity must equal 1, because it must be somewhere. So 1 equals, and we do the integration, and using the provided integrals, we're given 26244 pi a squared Bohr radius cubed. So a squared, and a squared is 1 over this, a equals 1 over 162 square root of pi, the Bohr radius to the 3 over 2. And just to add a little note beneath that. Right, moving on to answer C, the final part. The expectation value of r squared sine squared is here. We take the expectation, which is the integral, and we go through this. We're given these integrals anyway, which goes to 108 the Bohr radius squared. I hope all these very, very short brief tutorials exam revisions were helpful. I'll probably keep putting a lot more of them on YouTube in time, and go through a lot of actual course stuff as well, like proper tutorials. But these are just a very quick question answer sort of situation you get in an exam, university level quantum mechanics courses. So I hope these were useful, and please do subscribe, because I'll be putting lots and lots of stuff on applied mathematics on the channel and going through it as we go along. Thank you.